Let's keep studying these graphs, this concentration of reactants and products over time, because these graphs will give us, again, a very graphical view of the rate of reaction. One can define the rate of reaction, and that's actually how we're going to define it, is the change in concentration of either reactant or product versus the change in time. So that has an easy formula, because if we look at this graphs, one can just measure final concentration minus initial concentration, not absolute final, absolute initial, but for a given interval of time, you can just plug in how much has concentration changed in that specific range of time. Okay, so just by looking at these graphs, one can potentially measure this rate of reaction. So we can just macroscopically just consider, and that's how we indicate the increment with this delta sign, the increment of, or in this case, because if it's reactants, it's a decrement, so it's decreasing. Therefore, we can just define it as such: final concentration minus initial concentration divided by the time that has taken for that change. Notice that the rate of reaction is always defined positive. Always defined positive. So if what you're calculating is the increment of a reactant, because reactant is disappearing, this subtraction will be negative. This is why we need to put a negative in front, because we want to define the rate of reaction positive. Now, calculating it this way, it's easy, because one just needs to look at this graph and takes the values and do the ratio. But it has a problem. The problem is that because rate changes with time, this, depending on how large the interval of time we use, we will obtain a different value. Therefore, we may be interested in knowing what is the rate at a specific time. Using this formula, you cannot answer this question, what is the rate at a specific time, because you're using an interval of time. So if we want to answer the rate, if you want to find the rate at a specific time, we need to really make these increments very, very small, infinitesimally small. So what we do is, instead of the macroscopic difference, we do the limit of infinitesimally small increment of time that is called the derivative. So the derivative also gives us the slope, so we will define the rate of a reaction of a specific reactant or product as the slope of that of the curve concentration versus time at that point. And that means we are able to calculate the rate at this point, which will be given by the slope of the tangent line, of the line tangent to this specific curve. Notice that when we talk about reactants, this slope will always be negative, so make sure you understand that there has to be a negative in front, so that we keep defining rate of a reaction positive. So let's practice a little bit. Let's say that we're given this kind of plot here for the the formation of nitrogen monoxide and oxygen from the collision of two molecules of nitrogen dioxide. The first question is, at what time the following reaction is faster? The answer is that the reaction will be faster the more remarkable the slope is. So we have three possible times, T1, T2, and T3. So if you think of the slope here, this is smaller slope, and in here is a higher slope. So in all cases, at T1 being very positive or very negative, T1 will have the highest slope. So it's important to, one, realize that the slope tells us the rate of a reaction, and also that, of course, the rate of a reaction changes with time. Now, quantitatively, what can we say about the relative rate of reactants and products? Notice that the rate at which the reactants disappear is the same rate at which this one appears. However, if one is positive, the other one is negative, so we're going to put a negative in here. Okay? Why? Because there's a 2 in here, so these two will appear and disappear with the same amount, just changing the sign. How about oxygen? Oxygen will appear a half of its rate with respect to the rate at which the reactants appear. So if we talk about at what rate the oxygen product appears, well, if we said that this is oxygen appears much slower, or twice slower, or 1/2, so one needs to multiply by 2 to make it equal, right? So let's just, to make round numbers, if this is 1, this has to be 2, so to make these two equal, one needs to multiply by 2. So, and because this one is reactants, this one is reactants, and this is products, one needs to put a negative sign to make these two equal. So which one is the right option? If you notice, this is the right relationship at any point in the reaction between the speed or the rate at which nitrogen dioxide disappears and oxygen appears. Okay. Hopefully this makes some sense. We will keep using this notation, but this is just saying that the rate of nitrogen dioxide is negative the rate of oxygen, but wait, because the rate of oxygen at which it appears is half of it, we need to multiply this one by 2 to make it equal. Hopefully that makes more sense. We will keep practicing, and hopefully you'll get used to this somewhat awkward notation using derivatives.